EC'18. The first edition happened in 1999, Denver, Colorado. It was chaired by Michael Wellman. If you looked at the program of that conference, you would only see 21 papers, and I bet you would probably not recognize many of the names, but you would recognize some. So there was a paper by Thomas Sendhil, there was a paper by David Parks, so there was a paper by Joachim Scholler. So the conference changed quite a bit since then, but it still stuck to its roots. So it's been an annual conference since then, happening almost every year, so I think there was a 1 year gap in 2002. In 2014, the name was changed from ECM Conference on Electronic Commerce to ECM Conference on Economics and Computation, keeping the acronym but changing the name to better reflect the conference. As economics and computation is what this conference is about. Okay, so this year's edition, 2018, so we had a slightly large number of submissions than the previous year, 269 properly formatted kind of submissions that were not desk rejected because of formatting issues or something of that sort. So that's 269. Out of those, we accepted 70 papers. I'll give you more detailed statistics kind of about the kinds of papers that did better and the kinds of papers that did worse at the business meeting. So the general chair of the conference was Eva Dardash, who did an amazing job putting the whole program together, making sure that everything works smoothly. I would like to ask for a round of applause for Eva. So I'm Ithaca. I co-chaired this conference with Rakesh Vora, who unfortunately couldn't come here. So it became my job to do the opening ceremony. So all in all, it's a 5-day event, so it started with tutorials yesterday. We have 3 days of talks and other exciting events, followed by a day of workshops on Friday. Okay, so a little bit about paper selection. So this was the first year, at least in a long chain of years, that we used EasyChair. So the conference used to use ConfMaster as its conference management tool. As always, we had 3 tracks, which were roughly theory, AI, and empirical. We had a 2-tier program committee with 40 senior PC members and roughly 150 program committee members. Each paper was reviewed by 3 program committee members and managed by 1 or 2 SPCs as appropriate. So there were 2 SPCs assigned to each paper, but in some cases it really fell to 1 SPC to do the job. So the PC assignment essentially respected the tracks. I'm hesitant to say that it respected them properly, but by and large, if your paper was submitted to a track, you were guaranteed at least 1 SPC from that track, and you may have been assigned another SPC from another track if that was deemed appropriate for the contents of your paper. So this year we experimented with anonymous reviewing, and again we are going to talk about that in more detail at the business meeting, but this is just a brief summary of what we did this year. Okay, so special events. So in addition to regular talks, we had this year 3 invited talks. 2 formal talks with abstract in the proceeding by Sendhil Mullainathan, which is about to happen, and another one by Eric Budish, which will take place tomorrow, as well as a slightly more informal, but nevertheless very exciting talk by Vitaly Buterin. So that will be this evening, between 6 and 7. So we'll have test of time aboard, so that's Wednesday morning. We'll have an AGT test, so that's again an innovation of this year. So 3 papers from sibling conferences that were selected by program committee on the basis of being of interest to this audience. We'll have as traditional best dissertation award, and again for the first time we're going to have women in EC breakfast tomorrow morning between 8 and 9. Okay, so let me get to the exciting part, awards. So we appointed the best paper committee, which consisted of Eduardo Azevedo, Vangelis Markakis, Deposis Mishra, and Plenary. So appointing the committee was a difficult job because we had 11 or 12 papers nominated by PC members, and we could only appoint committee members who didn't have conflicts with those 10 or 11. Right? In a tight-knit community such as ours, this is a challenge. So out of those 10 or 11 papers nominated by PC or sometimes SPC members, the committee shortlisted 1. So you can find this information in the proceedings, but it wasn't on the conference webpage, so this may come as a surprise to some of you. Okay, so here are our 5 papers in sort of alphabetic order. So Muhammad Akbar and Shenguli, credible mechanisms, Omar Besbes and Amina Loa, prior independent optimal options, Mark Braverman, Jim Mauer, John Schneider, and Matthew Weinberg, selling to an non-regret buyer. Yilin Chen, Kaya Pradimata, Ariel Krakach, and Nisa Bishak, strategy-proof linear regression in high dimensions. And finally, Martin Luckner and Piotr Skowron, consistent approval-based multilinears. So out of those 5 papers that were shortlisted, the committee selected their best paper overall. And that award goes to Mullainathan and Sendhil Li, credible mechanisms. So if one of the authors is present, one of those authors are present, I'll be happy to present the award now. No, you've got me to do it at the published in the proceedings. And that award goes to Mark Braverman, Jim Mauer, John Schneider, and Matthew Weinberg, selling to an non-regret buyer. Take those to your homeworkers. Congratulations. Yes. So that paper also had a student as its lead author, so it gets also the best paper with student lead author award. And we don't have a separate award because this paper is eligible for it. So in addition to paper awards, so another innovation that we had this year are awards for distinguished program committee members. So that was a very difficult choice, but at the same time a very pleasant job, because we got to look at kind of best people who did a really good job. So as Rakesh said, so this restores my faith in the community. I tend to agree with him. So it was difficult to select best PCs. In fact, I didn't want to use the term best PC because it's impossible to choose a best PC out of 150. So we call them distinguished PCs. And we selected 3. So this award goes to Nick Karnowski, Dominic Cowie, and Matt Weinberg. I believe Nick and Dominic are not here, so Matthew, I believe, is around. I just saw you. I think. Okay, so if you don't mind coming up again. Tutorial chairs, Ithaca and and I also want to give special thanks to the mentoring workshop chairs, Nicole Malika, Rota Mehta, and Matt Weinberg. So I didn't get a chance to attend the mentoring workshop, but from what I've heard, it was a great success. Okay, so here are a few local organization leaders that I think everybody's in a better position to cover.
Okay, so a couple of things. Maybe you guys all met the coffee already out to the side. Session A will be in this room. Starting at lunchtime, you'll make it a little friendlier and the podium will be down there, but till lunch you're going to have to come up here. The B session is in 196, which is where the mentoring workshop was yesterday. It's off of the coffee room. And right across it, where some other workshop was, I forgot which one, is a breakout room open to all of you all the time. So we're basically occupying this space. The coffee for breakfast was actually an all-day coffee, so all-day food, so there will be coffee and snacks out there all day long. Maybe the most important technical arrangement, this is a small town, as some of you already observed, so the number of taxis, Ubers, lifts is kind that getting an Uber or Lyft to the airport might be problematic, so we recommend that you ride share. And the registration desk has a sign up for ride share. What I'm asking you is to write down which flight you're on, and we try to get enough cars so everyone can go to the airport in time. Please participate. There are not enough cars in this time. Okay, that was my spiel. And Edith can end this. Thank you.
Okay, so there are a few more people I want to thank. So one of them is Moshe Rabayev, previously EC chair, who really helped guide me through the process and made sure that I'm doing everything on time. Without him, kind of a lot of things wouldn't happen on time, I'm telling you. Okay, so I also like to thank, perhaps controversially, Lisa Thomas of Sheridan. Maybe I expect that I roll from the audience. Okay, so a lot of us had difficulties communicating with Sheridan, but this is only partially Lisa's fault. And in fact, Lisa was very proactive in responding to our queries very quickly. So I think she actually did a great job given the circumstances. I am personally grateful to her. At the same time, I'm very grateful to Scott, who helped us put together the conference submission template, which is something that Sheridan paid me. Okay. So I would also like to thank kind of local people who helped organize this conference. So that's in particular Makis Arsenis and Ayush Sefari, who designed the conference webpage, and also Vanessa Malley, who provided a lot of local support. Okay, and of course, so thanks both our sponsors who provided funding and other forms of support. So EC'18, which is kind of the main kind of body behind this conference, and our supporters, Facebook, Microsoft Research, Loop, Uber, and academic supporters, Cornell Department of Economics, Cornell Department of Computer Science, as well as Google. Okay, thanks. So I'm giving the podium to John to introduce the invited speaker.
Thanks very much. I want to add my welcome to EC'18 in Ithaca, New York, and add my thanks to the General Program Chairs, Ava, Edith, Rakesh, and all the other organizers and staff who made it possible and got the event off to such an amazing start. I'm also extremely pleased to introduce Sendhil Mullainathan as our first invited speaker at the event. Sendhil is a professor in the Harvard Economics Department and will be moving this fall to the Booth School of Business at the University of Chicago. Sendhil is one of the most distinguished contributors to the development of behavioral economics as a field, a subject he actually first encountered as an undergraduate at Cornell in the early 1990s. His work has provided some of the foundations of the economics and psychology of poverty, discrimination, financial decision-making, and a number of other core domains in which behavioral methods have had an impact. For these contributions, he's received numerous recognitions, including MacArthur Fellowship, membership in the American Academy of Arts and Sciences. Through this work, he's also engaged with government policy and the public through roles including Assistant Director of Research in the Consumer Financial Protection Bureau during the Obama administration, and is co-founder of organizations including the Poverty Action Lab and Ideas 42. And if you've ever served on a hiring committee or a government review committee, you've likely taken part in a training or prep session that has included Sendhil's work giving powerful evidence of the role discrimination plays in everyday hiring and selection decisions. Given Sendhil's interests in both human data-driven decision-making, it was natural as machine learning and data science began to grow rapidly over the past several years that he would turn some of his perspective to the ways in which they interact with the social behavioral sciences and with policy-making in general, a topic that he'll tell us about this morning. Please join me in welcoming Sendhil to EC.
All right. Can you guys hear me? Is this? Yeah. All right. Perfect. I think I left my clicker down there. This is not a good start. Thanks, John. Okay, so I wanted to just dive right in. I want to talk a little bit about algorithmic discrimination, algorithmic bias. And this is a topic that's very close to my heart. Let me start, before getting to algorithms, with how economists and behavioral scientists might think about discrimination as in society, and I think that will help shape how I'm going to think about, is this?
I think
The volume needs to be up. It's nothing that should I do this here?
Try that.
Hello? Hello? No?
That's that one.
Let's try this one.
That one's working. All right, let's swap it. Yeah,
Just swap that one out. How's that? Oh, all right. Here we go. I'm worried this talk is not worth all that effort. I worry we've set this up for failure. Nevertheless, let's just move on. Jesus, it's like a Goldilocks thing. So let me just talk through a little bit about how, as economists and behavioral scientists, we might think about discrimination, and it's going to shape how I want to approach algorithmic discrimination. This is the kind of thing that I think motivates a lot of people, which is across a variety of domains. If you look at the raw data, there are remarkable disparities between certain groups. I've picked race here, and for purposes of this talk, I'll keep talking about race, but obviously there are other groups of disparities we care about. Gender is a very prominent example, but we'll just use race as a placeholder. So here's an example where you look at unemployment, and you see there are huge gaps in unemployment rates between whites and blacks. Looking at data like this, I think one of the big distinctions that occupies social scientists, and I want to make this distinction early on, is what is the source of this gap? One reason we spend so much time on understanding discrimination is because there are two different explanations for this gap which have very different ramifications. One explanation is that African Americans are employed at lower rates because when they reach the job market, bad schooling or other things pre-job market lead them to have far worse skills. So they're kind of entering the job market with less skills, and so this is the natural consequence of that. The other possibility is that even at a level of skills that are equal, African Americans are hired at lower rates because of employer discrimination. This distinction is important because it isolates the source of the gap. Is it a structural problem entering in, or is it a behavioral problem at the time of hiring? So a lot of the work in social science goes towards distinguishing between things like this. One of the early things that we did with a co-author of mine, Marianne Bertrand, was to try to distinguish this. And we did this, I'm just giving you this so you get a sense of methodology. We did this using a simple experiment where we took a resume like this, or thousands of resumes like this, and we sort of sent them out to employers to see what the callback rates would be. But before we did that, we put names on them that are indicative of white or African American. Now, whether it's names or not, back then it was just names, but now people have tried to do this with photos on websites, et cetera. But what we wanted to do was create the conditions where we said, look, here are two people who are literally identical. So it's not an issue of African Americans were less likely to go to college, went to worse colleges, had lower skills. These are identical resumes. So now we're able to tease out the behavioral part of discrimination in this problem, at least at the employment stage. And what you tended to find was that African Americans would get called back at about a 6.45% rate, whereas whites would get called back 50% more. If you go back to the unemployment graph, that 50% gap actually explains the raw unemployment gap, because it means if this were the only thing that was going on, we'd see an unemployment gap of about 50%. For me, this was pretty eye-opening. I did not expect an effect this big. But it turns out that across many domains, experiments like this tend to show gaps this big. So for example, this is one of my favorite recent studies. So what they did was they posted ads on eBay selling iPods. And all they did was the same iPod. You notice there's a difference here. So a third of the conditions, they used white hands holding the thing. A third, they used African American hands holding the iPod. That was the only difference between the ads. And a third, actually, this is a funny treatment effect. They want to see the effect of tattoos. I won't get into why that is. Some sort of fetish, maybe, I'm not sure. They had some reason they cooked up for why tattoos really matter. And what they really want to do is everything else was kept the same, how they responded to the inquiries, et cetera, the objects being sold. And what they measured was how many objects were being sold. And what they found was that there was about a 3.8% sale rate for each ad here. At 3%, turns out tattoos hurt you a little bit. Don't get that tattoo on your arm. And African Americans sold at a ridiculously lower rate. This is the kind of evidence that I think permeates the last 25 years of the literature, in which nearly every domain that people have studied, they tend to find massive behavioral biases against disadvantaged groups. African American probably shows the biggest effects in the United States. People in other countries find different groups. There have been studies about Muslims in France, and gender biases in some domains are pretty large. So from this, what I think I take away is that there is an enormously large effect of bias. So what I want to now do is to try to put these problems into a simple framework, for now not including algorithms yet, but which just will help me make sense of what I think is happening here, and then I'm going to work algorithms into it. So what I think is happening is I want to think about a category of problems, and in this problem there are some outputs y, there's some inputs x, these are just variables. Individuals are defined by their y's, x's, and their race, and there's some decision we're about to make about these individuals, which I'm denoting by d. And in this case, we can assume that x is distributed in a biased way, so that is, there can be structural disadvantage, so that African Americans are entering the situation with worse x's possibly. And disadvantage can also show up in that the expectation of y given x can also be lower. That's sort of disadvantage in unobservable. So in the employment context, you might say even holding constant the resume, maybe the resume doesn't capture enough of the things that proxy for productivity, so there's still some bias left in the system. We don't have to assume these things, but you can. And notice, and I want to make this very, very clear, in the algorithmic bias literature, there's often a discussion of mismeasured x's. This way of writing it, there's no true x, so this includes the cases where there's some true x, and I've chosen to mismeasure the x in a biased way. Okay, and there's a lone equation. So what I want to, wow, this is way out of order. Let me start at the top. What I want to now think about is, in this simple context, I want to think of a class of problems where there's an outcome that depends on the decision. So I'm going to write that y equals yd. And there's an agent, say the person buying the iPod, the employer screening the resume, who's making a decision. In this case, the decision is, do I hire this person? Do I buy this iPod? And their payoff depends on this y. What will their productivity be? Will they actually deliver the iPod to me? Will I get screwed? So that's the yd. So the y depends on whether you bought from that person. And then there's a cost to deciding in this person's favor, the cost of hiring them, the cost of paying for the iPod. And the agents in this simple setup would simply like to use this sort of optimal decision rule, what's y1 minus y0 greater than c. And what I want to point out is this is sort of a simple treatment effect-like thing. What's the effect of the treatment? Of course, all these are unknown to the agent. All they observe is the x and the r. So for example, you see the resume and you see the race of the person. So this is a fairly general setup. To make any headway, we're going to want to focus on a specific category of problems where machine learning tools are particularly applicable. And this restriction, I think, is going to be super important, so I want to walk through it a little bit. I want to talk about situations where we want to assign this, we want to make this decision, and the treatment that we plan to assign, the benefit of it is monotonic in some y0. So let me walk you through why that case is important. When I'm thinking of hiring somebody, what I am predicting is, what is their baseline productivity? What will it look like if we hire them? If I'm thinking of admitting someone to a college, what do I care about? There's some earnings, y0, they have without college. There's some earnings they have given college, that's y1. I care about, let's suppose, I care about maximizing the treatment effect. That's the expectation of tau. It's not obvious why the treatment effect is monotonic in your earnings without college. There could be people who would have very low earnings but would benefit the most from college. So if you look at all the prediction policy problems, the prediction problems that we tend to apply machine learning to correctly, they have this structure, which I think is pretty important, which is that the decision to allocate these resources has to become a decision that reads like I'm predicting Y. And the optimal allocation ranks people according to my predicted Y value, and I give the treatment to people with, say, the highest Y value. Does that make sense to everybody? And that distinction is going to prove important later on. It also is going to prove important for scoping the kind of problems I'm going to talk about. There's a lot of situations where we worry about algorithmic bias that don't fit at all into this framework. For example, if we talk about chatbots, a chatbot could inherit a lot of discriminatory tendencies in the way it talks to people, but it has no decision that it's allocating. It's nothing to do with any of that. So this is a scope and a set of problems where there's some decision maker, an agent, who's making these decisions. We worry in a biased way, and we might want to have an algorithm in addition making those decisions. So yeah, so this image search results, chatbots don't fit into this. Okay, so in this case, what I want to think about is letting H be the human judgment of Y. And I want to point out a pretty obvious thing. What these data and other data show us is that for any real Y variable in this case, I'm going to make a pretty, I think, sane assumption, but possibly extreme, which is that the human prediction of Y, their race gap is equal to the true race gap, which we're going to call disadvantage. There is some disadvantage in the system, plus a bias term. So I'm going to assume humans are always biased against the disadvantaged group. In every context, we're going to live in a situation where the world is full of such bias. And what I want to say is the operating assumption is humans magnify whatever existing disadvantage there may be, and you can think of this as a preference or as a judgmental error, but this is the source. So they may not want to hire African Americans, they don't like them, they may misforecast their productivity. Whatever the case, this is the bias that humans have baked in. And it results in a choice rule where instead of choosing according to what you want to choose according to, there's an extra error term that's added in. Okay. I set all this up to say, even without algorithms, how would I think about discrimination and optimal policy? The typical approach here, I think, is to say, let's write down the social welfare preference function. Because now, when dealing with humans, we don't have the ability to engineer new rules. We don't have the ability to do anything. We just have to treat them as agents, and we have to ask, what is their choice rule, and how correct or wrong is it, and what can we do? So the policy framework for addressing these problems is we write down the agent's preferences. I've kind of run that. I write down their choices. I've kind of done that. And now I want to write down the social preferences, which I haven't done, and contrast that with what results when the agent optimizes on these preferences. So if we do that, I want to point out this approach is very utilitarian. I'm not going to bake in any preference that the social planner has above and beyond caring about the outcomes. The social planner is going to have some preference for outcomes, and the agent's going to either fail to achieve those or reach the optimum or not, and we're going to intervene to try and produce that. So notably, this doesn't bake in any process concerns. It doesn't bake in, by the way, I think John said to me, I should be careful calling this the social planner. I don't have any imagined universe in which there's a person who gets to plan the economy, and this isn't an operations research meets Mark's talk. The social planner is just a metaphor for there is a welfare function that we as society, through a complex legislative democratic process, have, and that welfare function is going to be implemented in our laws and regulations and our interventions. So this is just a metaphor for being able to clarify the preferences for society and how they differ from the preferences of the agents making the rules. Okay. But importantly, and I think this is where there's probably a divide between the algorithmic bias literature and the way social policy people might approach it, you start with the welfare function defined on who gets what and what are the preferences you have, including efficiency and equity concerns. And then you ask, what kind of policy interventions and decision rules lead to that outcome or fail to get to that outcome? So in this case, notice something pretty straightforward. I'm going to, by the way, I should say this, I'm going to ignore something pretty stark. I'm going to ignore the law, which you may say that it's probably not a good idea. But I think for purposes of this, it is actually an interesting point that we're stepping back from. I've just written down the social welfare planner. There's nothing else I'm going to talk about. And the reason is legal constraints in most of these problems are rarely sufficient and they're rarely necessary. They're not sufficient because in most applications and thinking about discrimination, it's not clear why the law even matters. What's being violated in the iPod purchaser situation? There's no obvious protected class and no person to sue, there's nothing, but there's still harm. So that's the sense in which it's not sufficient. But the law is also not necessary. People who don't operate in this area imagine the law as this ironclad thing that is given to us. Oh, you can't use race in the algorithm. Oh, you can't do. But these laws are derived, actually, and it's an evolving thing. In many domains, positive normative analysis, like this, has in fact shaped what the law has become. I think one of the most powerful areas in this literature has shaped torts, for example. Tort law very clearly, or at least certainly common law, but even physical law evolved. Consumer protection law evolved in response to analysis like this. Most law gets reshaped. And one of the points I'm going to make in this talk is actually we should get up above the law and start making theoretical arguments that then shape the law. Because I think in this area of algorithmic bias, that is one of the biggest opportunities we have, is to ask the question, what should the regulations look like? And we're only going to get there by starting from first principles of the social welfare function and walking down. Okay. So let's talk about the social planner here and get more specific. Suppose that the planner has race-neutral preferences. So ironically, this looks just like the agent's preferences. They also just care about the Y and have a cost C. But despite that, because of human bias, this creates an inefficiency and a motive for intervention, which is kind of interesting, which says even when the social planner cares about the exact same thing, because the human has this baked-in delta R bias, and the planner has no such bias in their decision-making, we now have a room to intervene. Notice that this room to intervene gets stronger if the social planner has an affirmative motive. So if their preferences are not Y0 minus DC, but they have an additional term of allocating the good, some equity preference for allocating the good to individuals of a particular race. I'm going to come back to this additional term. This can derive from deeper principles, such as diminishing marginal utility. So for example, if the disadvantaged group has lower consumption, you might say from a social welfare point of view, when they get stuff, the same dollar benefit, it's worth more. That's diminishing marginal utility. I'm not going to model that and leave that as this. But interestingly, a different reason this comes in many policy problems is because the benefit of the assignment is higher to society when we assign it to that group. Not in Y, but in something that's unmodeled in this framework so far. Okay, so when we have a setup like this, the additional motive to now intervene is we not only can undo this bias, but we can implement our positive affirmative benefit that we have for this group. So a lot of affirmative action kind of gets into this space of saying this is what we want to do because we want to push these groups forward for historical reasons or for other reasons. And from this, just when we're talking about humans, we derived a set of means of intervention. So for example, the primary means of intervention are aligning decisions through taxes and subsidies. If you look at the entire architecture of what we try to do when we implement anti-discrimination policies, they all have the form, oh look, there is a gap here in who gets hired. I'm going to tax hiring one group or subsidize the other group. We do this through enforcement mechanisms. When we see a delta, we try to dive in and do something. We do this through subsidizing certain groups. There's an enormous machinery, which you guys might or might not be aware of, which are subsidies for hiring, for giving credit to, for fill in the blank, certain groups that are disadvantaged. The other way we try to do it, and this is important, you'll notice, is to simply ignore this problem and to say, let's solve the structural discrimination that appeared upstream as we entered this problem. And the distinction between these two is very important because the human discrimination is only here in the bias term. If there's true disadvantage, the human is not making an error. There's still a problem. The problem is because we have an affirmative preference, but it's not a bias that we're trying to correct. It's that the situation is not the situation we would like. Okay. So finally, the third thing which I want to talk about in this literature is an interesting literature that tries to say, hey, why do all of this? Why add subsidies or taxes to the agent's decision? why not directly influence their bias? And that's probably the most interesting literature. For example, it starts by observing, and a ton of experiments have come in, and observed what are the things that generate bias. In employment, for example, one of the recurring themes as a big driver of bias is interviews. What's funny is lots of people love interviews, but in fact, interviews add a tremendous amount of noise and bias to the system. So my favorite study on this, which I'll just tell you about because it's interesting, is they bring subjects into this room, and they're supposed to interview somebody, and they either are interviewing an African American or a white candidate, and their camera is observing the interaction, and they measure all these cues, such as how close they sit to the person, whether they make eye contact a lot, whether they smile a lot. And the interviewer is dramatically influenced by whether they're talking to an African American or not. In fact, you have pretty good capacity, if you just saw the interviewer, to discern whether they're talking to an African American or whether they're talking to a white, just based on these cues. I mean, it's not an AUC of 1, but it's 0.6. There's some distinction. Why this study is so interesting is because they then went further, and they had independent judges rate how good were the interviewee's responses. Now, those judges only looked at the interviewee talking. And they found that these judges, even when they were looking at transcripts and couldn't judge the race of the person they're judging, found that the interviewee did a worse job because the interviewer created the conditions to create a bad interview. So this is an example of how the bias kind of evolves subtly in the mechanism. So one intervention people have had is to simply stop interviews. They're really just adding a ton of bias. Another intervention which works extremely well in the resume work is rather than having people read resumes just like that and pick good ones, you have them pick the 10 desired characteristics or 5 desired characteristics. Then you have them go through the resume and just rate on each characteristic. And then delete the resumes and then look at the individual things and say, oh, look, this one comes to the top on all 5. Because holistic judgments, oh, yeah, this looks good as a whole, is where bias creeps in rather than these individual judgments. And then I'll talk about one of my favorite ones in this. This is a study they did with musicians. When they came into play, people would judge, oh, is this, I know so little about music, I don't even remember, this is violinist? No. Do you remember, John? It's something. Let's call it violinist. It's not being recorded or anything. I can't be wrong. So they come in for violinists, and they listen to them play, and they judge, oh, who's the good violinist, who's not, for the orchestra. And in this experiment, what they did was they simply just put a curtain between the judge and the violinist. Typically, female violinists do much worse than male violinists, and people say, oh, well, they're just not as good. Put the curtain, and the gap completely disappears. So this is an extreme kind of intervention people have tried in other contexts. If you just blind the person to the actual characteristic you're worried about, that's a pretty powerful intervention. So these are all ways we have of instead of subsidizing the agent, taxing the agent, can we actually resolve the bias of the agent through much more brute force means. And so the gist of these interventions is make process as objective as possible. So this is where our story, I think, hits algorithms. Isn't it funny that the entire arc of this discrimination literature comes to this point where we say, oh, you know what would be really nice? It'd be really nice if we could just be objective. If we could just look at the variables that mattered, if we could ignore it, we would just be objective. But after all, that's what algorithms are meant to be. And I think that's where a lot of the early work on enthusiasm for algorithms is quite connected to a very deep psychological literature. Independent of algorithms, there's a whole literature that says the best way to reduce bias in society is to impose rules, objective rules, rather than having human discrimination. So rules protect us against human capriciousness, which shows up as bias. So there's an entryway into this algorithms literature, which is kind of an interesting entryway, starting at the bias of the human, forgetting about the bias of the algorithm for 1 second. And today's talk is really, I think, about a couple of waves. I think there was wave 1 in this literature where you might feel, I would feel, wow, If you look at everything I've just showed you, say algorithms can do a lot of good, a lot of social good. If you only care about gaps, discrimination, algorithms are it. I think we can call that wave one. Then you have a set of things that have emerged, which all of you are familiar with, which is algorithms can do a lot of bad. They too can be biased. And if you look at the broad literature right now, I'd say we're in this sort of wave two. We're seeing all the ways in which algorithms can kind of screw things up. What I want to argue in this talk is that we should move to a wave three, or we are on the verge of moving to a wave three, which is by unearthing the specific problems that algorithms can generate and marrying it with what we thought in wave one, I think we're on the verge of saying, actually, if we apply them at the right time and in the right way, they can do a lot of good. A big set of errors fall if you apply them the wrong way, that you might apply them into the wrong context. But do it correctly, and I actually think we're on the verge of going to a new equilibrium where we've done enough now about the problems of algorithms to realize the original vision that's behind the human bias. And if I were to summarize this just so that you get a sense of where I'm coming from, I'm not trying to be naive about the problems of algorithms. I think I'm just trying to be sophisticated about the problems of the human mind and say there are places where algorithms can help a lot. So that's where I'm trying to get to. It's not to say, and I'm going to be a lot of what I'm going to talk about is actually applying it properly. What is the scope constraint? Where do they apply and where do they not apply? But we should be thinking about, wow, we can really make the world a better place if we do it correctly. So let me start with a particular problem where I think we've tried this application, and then I'll talk about expanding the model we had right now to think about algorithmic bias. So this problem starts with, in criminal justice, there are about 12 million arrests every year in the United States. And shortly after arrest, by the way, I don't know, would any of you have guessed this number, 12 million? Is that the number of zeros? I did not know that many zeros. That's a crazy large number. Right after arrest, people go in front of a judge, and the judge has to make a decision for them. The decision they have to make is whether they wait for trial in jail, or whether they get to wait at home. Now, this is a pretty big decision, because if the judge says you can't go home, you have to wait for trial here, that's about a 2 to 3 month wait. So if we go back to costs, that's an enormous cost to the individual. Just to put this in real terms, think about the fact that at that point, your job is gone. You're basically unemployed. There's no way you're keeping that. But 2 to 3 months, a lot of your things are eroded. What if you have kids? What if you have a family? What's striking is in some jurisdictions, the average wait is 9 to 12 months. These are not people who have been found guilty of anything. They're just waiting for trial. Now, who knows where we should set the threshold, but wherever we set the threshold right now, we're ending up at about 750,000 people in jail. So in a paper that we've done, we simply just said, hey, it's funny, this is a prediction problem, because the key to this is that we want the treatment effect of jail to be monotonic in Y0, but the nice thing about jail is its treatment effect is known. We know the crimes you're going to commit while in jail. None. So if you actually just take the derivative, the treatment effect of jail is exactly monotonic in your base rate crime risk. So that's a sense in which this is a pure prediction problem. To decide who we should jail, we should just predict your propensity to commit crimes. Now there's a lot of subtlety, how do we predict? I'm going to ignore that for this talk. I'm just going to point out something, which is the judge, in fact, is just a prediction engine. Give me the defendant history, make my forecast whether they'll commit a crime. Of course, that's exactly the kind of thing we can build an algorithm to do. Give me the XR argument. When we do that, like I said, I'm going to ignore a lot of subtlety here to just get to the race issue. When we do that, we found that we can rank individuals according to their crime rate and then decide at any release rate what would be the realized crime. The highlight of this is that if you look at judges, they release about 73.7% of people. And the algorithm at that same release rate results in about 8.5% crime, whereas the judge at that release rate results in about 11.3% crime. So this is a sense in which the algorithm can dramatically improve social welfare simply by rank ordering people better. I actually think that reducing crime by 25% is even less impressive than if you were comfortable with an 11.3% crime rate. Why not go in the right direction? Why not say, great, let's release people until we get to an 11.3% crime rate? Then we can release 84.6% people, which means that we reduce jail populations by 41% just by re-ranking. So take a result like this. I haven't talked about discrimination. This is a kind of standard deployment where you might say, when I look at efficiency, algorithms give us a lot of efficiency gains. It's also the kind of situation where you worry about racial bias, because you'd say, yeah, judges here could be biased, but human bias in this data set creeps in at so many levels. For example, this is some of the data that we used. Notice one of the data we use to predict is the defendant's prior arrest record. How many felony arrests they've had, how many felony convictions, how many misdemeanor arrests. So you should be worried that since I said every variable in our data set is prone to human bias, you should say, yeah, cops arrest African Americans at higher rates, so their past records look worse. So the algorithm could, in principle, be doing much worse and actually exacerbating all of the bias in the data. So I think that's the concern, that given that all the inputs are biased, we are going to end up with potentially aggravating the racial bias in the data. So let's look and see what happens. So the judge releases, I'm putting here the jailed rate, sorry. For the jailed rate, they're about 31% black, 25% Hispanic, 28% is the jailing rate of these groups, okay? So you can see African Americans are jailed at much higher rates than the other groups, exactly as you kind of imagine they might be. Now, remember when I said the algorithm could achieve the same crime rate as the judge? When it does that, it's got the same crime rate, 11%. But notice it's jailing African Americans at a 19% rate. So off the bat, African Americans are dramatically helped by this thing. It's kind of a funny way to look at this, because notice what I'm saying. I'm saying if the efficiency gains lead us to release more people, guess who that benefits the most? The people who were jailed the most. So weirdly, before I even get into the issue of, quote, is the algorithm biased, it's an immediate observation that efficiency gains help the disadvantaged group when they're the ones being, yeah.
You said overall there was about a 41% drop in the jail rate. And if I compare 0.3101 with 0.1899, it seems like about 41.
It is, exactly. And that is the point I'm making. In other words, if you have a social welfare function where what you care about is harm, and you care about harm to the African Americans, there you go, 12% less African Americans in jail overnight. There's an... Exactly. So, but I'm trying to bring that out exactly. In the next, yeah. So I would love it if at this point I hadn't taken relative versus absolute into account. This would be great. But I'm trying to put it in these terms to make it as stark as possible, which is to say, before we get into the minutiae of relative harm, the welfare function is defined in absolute harm. So we should actually calculate the absolute harm first. And we may say, you know what, I don't care about absolute harm. But I just want to point out how extreme of a statement that would be. You would be saying, African Americans have a 40% less chance of being in jail. None of that matters to me. I only care about the relative rates. That's a pretty extreme statement. We may have an additional care about relative, but I just want to point out the absolute benefits are enormous. And I think that by not writing down the welfare function, but instead writing criteria of algorithms, the algorithm should be relatively fair, et cetera, we forget the enormity of the gains that come from the level. Now, let's look at what happens in relative situations. The algorithm, if we use our usual ranking rule, if we just stick at the same release rate, now we're not going to get any of the benefits that we would get from that. We're going to look at the relative. It jails a smidge more African Americans, a smidge less Hispanics, and about the same minority. So in a relative sense, you could say, oh, there's a tiny relative harm of African Americans, tiny relative gain for Hispanics, and no effects of the minorities. Even this I find kind of interesting because we could always jigger the algorithm a tiny bit and say, well, I want to match the judge on race. I want to get their same thing. And if you were to do that, you get exactly 0 effect on the ranking. So to some sense, a good way to put it is there's no effect on the racial composition, and you can get the same efficiency gains, or you could actually get all of the efficiency gains, release a lot more people, and get the same absolute benefit. So the relative in this case is minimus. I'm going to skip this for 1 second. So this example shows something funny, which is without question the data has bias, yet for 2 reasons we're going to end up reducing bias. One is the human judgment is more biased than the data. And 2, there is just a disparate impact, in this case a disparate benefit of reducing overall jailing rates. And I want to point out that this is an underappreciated argument, I think, in the literature, which is that human bias, when we're comparing the algorithm to the human decision maker, creates an arbitrage opportunity for the algorithm. It sets up individuals who, for a given Y level, are being jailed at higher rates. At a given Y level, are being hired at lower rates than they should, which in turn, the algorithm, by looking at Y, is only going to pick that up. The upstream bias actually makes the groups unequal and benefits us here. And a general result, which I'm not going to go into, but with just the framework we've built so far, using a predictor from an algorithm generally tends to help the disadvantaged group in this kind of setup. And you can see why, the way I've set it up, the only thing that's going on is the human is adding bias delta. And so it's in our interest to get rid of that bias delta. One way to see how this plays itself out is that if the social planner has additional equity preference, if you say, I'm not interested in only doing as well as the human judge, I care about equity above and beyond the human judge, then we can just adjust the decision threshold using the same ranking. So here, I take the same thing and I say, okay, well, screw the judge, I actually care about equal release rates for all races. So now I'm going to get to perfect parity so that the jail rate competition equals the base rate. And then you can simulate out and see what, in this case, it turns out that that has very little effect on efficiency. In fact, it has almost no effect on efficiency. I just want to pause here and just show you this number here for a second. I think that you can make sense of this disparate impact thing up here by saying, oh yeah, you're releasing a lot more people. This number where I say all I've done is equalize release rates for African Americans and whites so that it exactly matches base rate, so there is no racial bias in jail. And I still get almost the same efficiency gains. It's a little extreme, but in fact, in a lot of applications, that's what we find. I think most people come in with the prior that what's going to happen is that when we do this, we're going to lose a lot of efficiency gains, which in turn must mean they think a lot of the efficiency gains in the system are coming from discriminatory tendencies. If you believe in a world of upstream bias, algorithmic arbitrage in this case tells you that actually there are a lot of African Americans who are in jail who shouldn't be in jail given their crime rate, which in turn tells you if I try to equalize base rates, it's not going to cost me much, if anything at all. So I just want to point this out because I think that this is a much more positive perspective on how algorithms can reduce bias than we tend to think of. Having said this, these results all rely on something very crucial, and which is counterfactual in some applications. They rely on the fact that the algorithm and the social planner agree, the agent and the social planner agree on the right Y variable. That is, the planner's preferences are on Y, and the agent's preferences are on Y. I think this resonates in pretrials because in pretrial what we care about is flight risk. That's what everybody cares about. But in other cases, the planner may care about an outcome W, whereas the agent cares about the outcome Y. None of what I've talked about applies to this case because the agent is busy ranking on Y, the algorithm is busy ranking on Y, the planner's like, I don't care about that variable, I care about this variable. Let me show you an example of this that shows up, just to get very concrete, that Ziad Obermeyer has some recent work on, which I'll show you. So in this example, it's a very specific example in health, though albeit a pretty important one. So there's a lot of hospitals living in the United States. I guess I feel like I'm walking you through all the ugly parts of US social policy. We've done jails, and now let's do healthcare. Next up, I'm doing immigration. So hospitals in general seeking to improve the efficiency of care, which is code for lower costs. One of the things that they tend to do is they tend to say there are these high-cost patients who have diabetes and heart disease and all of these problems, and what they tend to do is they tend to show up at the ER and when they have a problem, but they're not sure whether it's a big problem. We should take these people, this group of people who are very sick and going to have consequences, and put a program in place. These are called care coordination programs. Give them like a nurse. And instead of showing up at the ER or going to the, they just call the nurse whenever they want. And it turns out that treatment control studies of these programs have shown that they're somewhat effective because it's much better to have a point of care for someone who's going to have a lot of calls and a lot of conditions. And it seems like it both reduces costs and increases health. Of course, we can't give care coordination to everybody, so we need to target it. And there's an operating assumption that the way we're going to target it is who needs these programs. The benefit, the treatment effect of these programs is proportional to baseline cost. So algorithms have been designed to predict baseline costs and target the program to people who have high baseline costs. So let's see at the racial bias of one of these algorithms. On the x-axis, I put the algorithm's risk score, which is what's used to assign people to these programs. On the y-axis, I put the cost. And you'll notice that whites and blacks, this thing lines up almost perfectly, their realized costs. If anything, actually, at the same risk level, there's a minor, slightly higher cost for whites, which means that whites are being biased against in this program. It's a very minor effect. So what this says is, oh, interesting, there is no racial bias in this program. If I went back to what I did before and we did the Bayes analysis, we did this whole thing, we'd say, oh, look, this algorithm in terms of ranking costs doesn't do anything particularly badly. But there's a problem here, which is it's not clear we should just be ranking on cost. And you already start to see this problem if you say, hey, let me decompose costs. Let's look at outpatient costs. That's weird. So in outpatient costs, actually, at every risk score, blacks actually have lower cost. Well, that looks like favoritism towards whites. But then you look at emergency visit costs, and you're like, oh, wow, this is a huge racial gap. So you had these two cost variables that were being summed up. And when you summed them up, you had no racial bias. But in each of them, there was a bias in opposing directions. Why does this matter? Let me skip this for a second. The two kinds of costs are not equal. We care about reducing costs, which means we care about the preventable costs, not about the predictable costs. And arguably, the treatment doesn't reduce all costs. It reduces emergency room costs. It reduces those type of things which people should not be showing up randomly for. And blacks have more of the latter. So if you thought we should be predicting emergency room costs, actually the algorithm is doing a very bad job. And so a way to think about this is that we don't care about predictable risk, we care about modifiable risks. And outpatient costs are not modifiable, emergency room costs are modifiable. We just predicted the wrong variable. But actually, in part, this is a misspecification problem, and this shows up, I think, tremendously in a lot of these sort of interface of algorithm between human decision making. What happens is the algorithm designer goes and says, hey, who are you looking for? They say, oh, the high cost people. Great, I can predict cost. The conversation is a little too pallid. You need to dig much deeper into exactly what the variable is. But the truth is, I'm sort of sugarcoating it. Even if we predicted ER costs, that's not going to solve the problem because hospitals care about costs. The social planner cares about health, not just cost. Even if the hospital had predicted ER costs, we shouldn't be satisfied with that at the social welfare level. We care about the health consequences. And so when you look at it from the health point of view, the gaps are enormous. At every risk level, if you look at diabetes, renal function, blood pressure, African Americans are much worse health. So if the point was to target people at low health, even if you got ER costs, African Americans would be grossly under-targeted. And this goes back to the Y variable, cost, versus the welfare variable, W, which is health. I hope you guys all see, I haven't said explicitly why there's this gap. It's a pure access gap. African Americans have less access to medical care. So at every health level, they simply just have lower costs. Doesn't matter how you count it. And you can see this at everything. So the consequence is that we have this neglect. We think a lot about these inputs, but we're less so exact about the outputs. Okay. So W and Y, I think, is the bigger and biggest problem here, is that we've got these, people call this bias labels, but bias labels are just a subset of this. It's not bias labels, it's that, for example, a police department may care about clearance rates, so they care about arrests. The social planner cares about reducing overall crime. There's not arrests that we care about. A school may care about test scores. Society cares about general human capital accumulation. And one of the consequences of this is that there are very different objectives a social planner may bring to a problem than the agent. So for example, search results might be optimized for click-through, but not for the social impact of certain people seeing certain ads. And so in some of the search results for jobs, you could see how just optimizing click-through will produce a result that's optimum, it does great stuff, but not for the variable that's in the objective function. And the most extreme example I find of this is when we train the algorithm on human judgment itself. We don't care about human judgment. In medicine, this is very common. You train on diagnosis, but diagnosis is the human judgment, not on the ground truth. In all these cases, the big problem is the welfare function has W, the agent has Y. So wrong variable leads to the wrong ranking. Instead of ranking along Y0, we have this additional problem. So this creates a prediction externality, which is we're predicting Y when we wanted the treatment effect of W. And I want to talk about that as being, I think, the core threat to applying algorithms is not properly taking into account this externality. So one observation is this prediction externality in lots of these cases can have this disparate impact. It can be bigger for some groups than other groups. And I just want to observe for a moment, we've opened the door to this thing, but it really doesn't have just to do with race. Once we're predicting the wrong variable, there's huge welfare losses to be had, some of which are felt by race, but there are many other group differences. In the example I just gave, predicting health rather than predicting cost rather than predicting health has huge consequences, even if you didn't care about racial bias, because you're just predicting and ranking on the wrong variable. And that type of prediction externality, I think, is pretty important. Okay, so this seems to have a pretty easy solution. Let's just predict W instead of predicting Y, or incent the agent to predict W. And I want to kind of suggest the problem runs deeper than that. The first thing I want to observe is that even though Y satisfies the condition of being an assignment problem where the only thing you care about is prediction, W need not. There's no reason that from the social planner's preferences, the treatment effect is in any way monotonic in expectation of W0 or in Y0. So the example that I often have in mind of this is take college admissions. Let's say you have a college that wants to make sure it doesn't have people dropping out, so the Y that they're predicting is ability to get through college. So they predict that, they rank applicants, and they want to make sure they don't admit applicants who are going to fail. Okay, what might the social planner care about? Well, obviously the social planner cares about the social return to education. So they care about your income earned if you don't get educated minus your income earned if you do get educated. That's the tau W. There is no reason that that tau W has to be monotonic in anything. In fact, we don't even know who's going to have the highest return to education. Perhaps an African American who is very highly skilled would have the highest return to education even though they have the lowest wage if they don't get educated. So there's nothing about this problem in college admissions. So when we talk about college admissions generating an algorithmic bias, I think the bias there runs far deeper. There isn't even a prediction. We're taking something that should be a causal inference or something assignment rule and mushing it up with the prediction problem. Predictive policing is the other case. People talk about how these algorithms in predictive policing, we assign police to where crime rates are high or arrest rates are high, and arrest rates are high in these neighborhoods, even conditional on crime, and maybe that induces a bias. But that kind of misses, I think, the forest for the trees. If you think of predictive policing, your goal is not to assign to places of high crime. Your goal is a deterrent effect and in equilibrium reduce overall crime. So it's not even obvious that for purposes of overall crime, we have a prediction problem. Predictive policing has a deeper problem than simply just, I'm looking at arrests and not true deep crime. It's that once I think about true deep crime, I've failed to satisfy this condition. So that's the first observation, once we think about Y versus W. Second observation is, of course, if it is a prediction policy problem and W is available, sure, just predict that. The problem is, of course, W is often unavailable. We don't know true crime. We only know arrests. And then I think here the case is triaged into two important cases. One, what does the human predict? If the human here is actually knows and predicts W, for example, if what we care about when employing somebody or admitting somebody is some net gain to them, and the college admissions officer is actually trying to take that into account and not just admissions, and we automate the system and simply just predict dropout rates. We had a human predicting W, and we have an algorithm predicting Y. In that case, the algorithm can actually make matters worse, even if the human were initially biased. And that's, I think, a pretty important case, because notice you went in thinking you're going to get rid of this delta R, but by predicting Y, you actually have you've kind of introduced this externality here by not predicting this difference. Okay, so and I want to, we've in other work called this omitted payoff bias, and I think this kind of is important in a large set of applications. It's wider than just algorithmic bias, as I said. Probably the most important ones I can think of are employment and sentencing. When we have all of these rules as to who to promote, who to hire, these algorithms always tend to predict a very mechanical variable, or job performance. What does job performance mean? It's some rating on some scale, or job turnover. There's no way that the W that the agent or society cares about is that very narrow Y variable. So you can do well on that very narrow ranking, but do badly on overall welfare. Criminal sentencing is another good example. It's not clear it's a prediction policy problem, but even if it were, it's not clear the only thing you care about is some narrow recidivism prediction when making sentencing. Even the judge cares about more than that. Okay. I think in these cases, we even make the error whether the algorithm is even beating human decision making, because the algorithm is predicting the wrong variable and doing the wrong ranking. Finally, I think the best case scenario is humans are also predicting and choosing based on Y, and then we get back the original dominance results. It's too bad that you're not doing W, but at least you'll beat the human. So got a couple of minutes, should I? So the pretty general result that I want to kind of get to is, I'll skip this. There's a simple way to think about all of these results that I've talked about. I think it's been helpful for me to go back and ask the question, why would you not want the expectation of Y0 given X comma R as your starting point for the ranking? Because after all, that is what the algorithm, any asymptotically consistent algorithm, is giving you that number. Even in a world of bias, that number might be biased, but if it's biased, you can always undo it by simply changing in the decision rule the thresholds you set. And when we care about W, we can start with that number and adjust by our priors. The only thing we wouldn't want is a situation where the human is doing this adjustment much better than we are because they have W and we don't. But this, I think, captured at least my understanding of all of these cases. So let me do the waterfall and then stop. So W is not a prediction policy problem. Terrible application case. W is a prediction policy problem and available in the data. Great, predict W instead. It's not available in the data, but the human is optimizing it. Terrible use case, because the human is actually optimizing the right variable and you're optimizing the wrong variable. And a lot of applications, I think, fall into this bin. And then there is a set of cases where it is a prediction policy problem. It's not available in our data. The human's not optimizing on it either. And actually, the algorithm gives us a lot more control in these cases. OK, so let me start. Let me skip this, because I think this is not. This is a set of results that I'll. Oh, look at that. Look at that. They're really. Did you see this one? Isn't that impressive? Anyway, moving on. So the first one I want to say is that, to conclude, I think the first lesson I'm hoping to pinch here is that we should be analyzing these algorithms as objects with the social welfare function, and that could give us insights to where the use cases are highest. You'll know, the second one is I think it's important to separate the algorithmic bias into several components. I think we tend to think of the entire procedure as algorithmic bias, where we say there's training data, there's an individual that comes, the algorithm takes the training data, and then the individual makes a decision about that person, and then talk about the bias of that. In fact, I think actual machine learning estimation is one part, and decision rules that rely on ML are another part. And so I actually think we should be thinking about bias in this setup is to what extent are we thinking about bias of the prediction algorithm, and to what extent are we thinking about the bias of the decision rule that this algorithm feeds into. And by and large, I think what I'm taking away from this literature is that, oh, sorry, I'll say this, is that the bias of the prediction algorithm is very much focused on issues where the wrong variable is predicted. The bias of the decision rule is much more in the cases where we just can set different thresholds for different groups. Okay, the final lesson I want to take away is, I started by saying I'm going to ignore the law, but I want to end on this and say I actually think the regulatory legal framework is going to be set in the next 2 decades. I don't think we're at the point where we know even simple questions like, should algorithms be allowed to use race in making decisions? Should a credit scoring algorithm be given access to race? Might it actually be good if it's given access to race? Those are questions that are up in the air, I think, in the next 2 decades. I think law and economics has been successful in shaping those discussions. But I think in this case, computer science, law, and economics together can ultimately shape this new framework. And I think ultimately, many of these questions are really welfare decision theoretic. And I think it's even an open question, and there's really interesting results on this, where something as simple as we should be letting the algorithm use race under these conditions that is actually good for the low-income groups. That's entirely possible and within the set of results that you're seeing here. So let me stop there. Thank you. Should I take, yeah, I can take a couple of questions. Yeah.
When you compared algorithms to judges, you talked about crime rate, but presumably we also care about the severity of the crime. Is there any data on that?
Yeah, because you know which crimes, such as violent crimes, murder, rape, and robbery, and that's a case where actually the algorithm does even better against the judge on murder, rape, and robbery, for example. And if you sort of go back to human bias, then that's kind of ex post obvious. I didn't know this going in. That's because what are the things humans get relatively wrong? It's the harder to predict, the rarer events. So in fact, on those, you beat the judge by a lot more, so, using the same predictors. Yeah. So I think I misspoke. So the question is, why not look at total expected number of crimes? I think that is what I was trying to do when I said, let's hold the crime rate constant. By rate, do you mean crime rate in the total number of crimes in society? Yeah, I should have said in that graph, that is what I meant by rate. It isn't the rate in the released population. I was trying to do the welfare calculation on the y-axis. So it's not the rate in the released population. It's the total rate in society, exactly for the reason that you're saying. It's so that it's a level effect. Yeah, I should have been clearer about that. Thank you. Yeah.
Has your algorithm been adopted?
I mean, we're looking for good parents right now. No. There are jurisdictions that have been starting to roll out, and there's one jurisdiction that's trying to roll out a tool like this. I think one of the things that is very intriguing in those conversations is once you get to deployment, it becomes much clearer that the city's preferences can be different than just the y variable that you forecast. So they clearly have preferences over racial equity above and beyond just the y variable. They clearly have preferences for other outcomes above and beyond failure to appear, which is what the law says. So I think in the rollout, it becomes clear you have to start figuring out how do you put in different thresholds or bake in these other things. And so that's what's happening right now. My best guess is it'll be rolled out in the next year or so. And then we'll see. Should we? Yeah.
I think in any way there's the hypothesis that the judges are maximizing the social welfare, not the why, and that's reducing the cost of city partners.
It's a great question. So as part of the rollout, one of the things we're trying to do is, and maybe this is a general case in other places that you would want to deploy. I think to enrich the conversation, between what's the variable we predicted, what's the variable the agent cares about or society cares about. We're trying to bake in a part of this, which is before they're even given the tool, which is to go back and do a bunch of look-back analysis and say, okay, you released this person, write the reasons why. And that can and has been proving somewhat illuminating. For example, some judges will say, well, they have a family, which then tells you that's not a forecast of a Y, it's a preference of a W. And so I think in general, rather than asking what variable in general should we be predicting, going case by case and asking what were the considerations in this case and try to bootstrap up to a W I'm not saying that they maximized well, but at least you know they have goals other than what they listed. Yeah, that's great. Oh, yeah. So there's a little bit of qualitative work that people have started to do. Cynthia Rudin has done some interesting work on this, and I think that's an area where a lot more can be done, because I don't think we've yet brought the behavioral science machinery to how do you meaningfully have a conversation between the judge and what they're looking at. So just to make it clear, I think, for example, we want to know how do you even show the information in the algorithm to the judge in a way that they can make sense of it? And that would seem like a question of interpretability, but I think it's much more complicated than that, because what humans tend to find interpretable is not necessarily, a simple rule or whatever it might be. Humans require a lot more massage to help them interpret it. So I think we're only starting to see those type of things where you present the rule back and see what you get. And I think I think we're seeing early deployment, like the healthcare deployment algorithm, deployed early before we even started to have those conversations of like, hey, so it's already being used before we even can kind of know what the constraints are. Hey, check.
How do you know that the 8.5 mistake is a result of that optimization and not the result of just a mistake in estimation?
Do you want to just say one more word about what the difference between bad optimization and mistaken?
Most of the judges see something that's not in your data. If the 11.3% is reality, the 8.5 is something that you estimated.
Oh,
Maybe the
totally.
estimation is just a mistake.
Oh, yeah. One thing I went through, because I didn't have time, is that arriving at that number or numbers like that, one has to be insanely careful, because I can't simply just say, these are the people I would release. I'm going to make a guess as to their jail rate. And so the bulk of that work was not giving the algorithm an unfair advantage over the judge by saying when the algorithm releases someone who is jailed, someone for whom we don't have a label for, the algorithm gets to create its own score, because that would be a ridiculous way of doing it. Yeah, and I agree with you. Yeah, and so the bulk of that paper was making sure that's not what's happening, using a set of techniques where we have plausibly exogenous variation in who was released and who was not, and then validating the algorithm. That's a problem that appears in this whole literature, is that you've got to be careful of that selective labels problem. Good. All right. One more? Hi. Yeah.
So I really like the resume example. It's one of my favorites when I'm talking to people about like ways that bias fits in. But one thing I'm curious about is whether people try to tease out whether your name, which may give some indication to your race, your class, or your gender, actually provides additional signal conditioned on everything else being equal in some hiring or other area.
Yeah, there's been work along these lines. I think what's difficult is if we took just that study, it proves very, very hard to do more than that, because there's no other way of communicating race. So I sort of take variants of that study that try to find other more subtle ways of communicating race, make it hard to interpret, because I don't know if people even took race away from the resume. What I take more hard in is studies like that, but that instead of even looking at name at all, they simply just attach photographs. And those studies tend to find. So I would say that study is a bad early version, and if I was thinking of the best later versions, it's ignore that study and look at studies that have used photos, because now in online applications. And those studies don't have the important confound of socioeconomic status. except to the extent that African Americans are of low SES. And those studies tend not to find, tend to find the same gap, basically. So, should we? Okay.
Thanks again.
Thank you.